Hello, sorry about the slow start, but I'm here to talk about the role of technology transfer to improve fertiliser use. There is a paper in the journal. Although Ian and I wrote the paper, this talk is going to represent the whole of the department that is the New Zealand Centre for Precision Agriculture. This is global fertiliser use. From 2012, those figures are projected. So what we're hoping that we can actually alter those so the projection and the line becomes more horizontal. Farmers are seeking to improve nutrient use efficiency. Now, in the developing world, this is caused by the fact that the more you put on, you get a cost-benefit asymptote where you're not getting much benefit and you're just increasing cost. Also, fertiliser that's not attenuated in the crop ends up becoming pollutants, nitrate and phosphate into waterways or nitrite into groundwater. Farmers the world over need to make better decisions because those unfortunately in the developing world often don't have very good decision-making tools. They do not have soil testing facilities, they don't have the labs, the wherewithal to get information on their nutrient status. And unfortunately, they use the fertilisers and manures they've got, which may not be fixing the limiting factor. In rice production, for example, in some areas of Asia, South America and Africa, rice production has been doubled by applying potassium chloride, which where potassium was a limiting factor, but farmers were applying nitrogen and DAP and in fact weren't curing what was the nutrient that was limiting their production. Remote sensing, well, it can be done proximally with machines that are next to the ground. It can be subterranean using ultrasound. These are two satellite images that I downloaded freely from Landsat 8, and which has 9 wave bands, multispectral bands, and 2 thermal bands. The picture to your left is a thermal image of one of our research farms. That's a 6,000 hectare property in the centre of New Zealand. The resolution is 30 metres and there's a temperature map taken in March, and the areas in red are the highest temperature and the areas in blue the lowest. And the one to the right is an NDVI map, that's normal digitised vegetative index map, and that was taken in June. The interesting things that dealing with crops, it's a pasture, so we're dealing with pasture, not crops. So it's a perennial pasture of mixed species, so it's changes throughout the season depending on water, and the areas in red where there was very little edible matter or quality matter changed in the winter, which is June over in New Zealand. So the areas with the highest NDVI, in fact, had the lowest NDVI in the summer. Hyperspectral remote sensing offers more tools for dealing with what is actually happening in the nutrient, and we're hoping to improve fertiliser use efficiency, especially in hill country New Zealand where fertiliser use has been under-applied and production has been falling. We want to arrest that without creating any environmental damage, and we certainly want to try and maintain current spending but get better bang for the buck. So we're looking at and doing hyperspectral imaging. This technology is coming into agriculture now. It was originally military technology so that people could actually see camouflaged vehicles, armies and everything else they wanted to see because it wasn't dependent on visible light. we're trying to find the information that we need from the cube. We're using a Cessna 206. We have an Asia Phoenix hyperspectral sensor which fits in the aircraft. It has 2,200 wavebands, very high resolution, very low number of false readings. We process the data using software. We're using ACT Core 4, which is from, I think, the University of Zurich. What we're looking for is the shortwave infrared information, so we can actually see the nutrient. The NDVIs and other quality indices look at the red edge and the near infrared. So when we get into having a lot of short wave infrared information, we can establish what nutrients actually in what we're looking at. We need to correct the information, so what we have, we geo-rectify it so we know where we are on the ground, and we change from a radiance to a reflectance, and then we classify out all the buildings, roads and bush areas that aren't pasture. That is a map taken from the aircraft that's been geo-rectified, and that's the farm Erewhon. These next slides are not Erewhon, but we've got 4 research farms. This is one that we have actually completed and done some ground proofing. All the information that we establish here has been ground proofed to some extent, because at each farm we visit 4 times a year and we take 400 pasture samples. We take 400 proximal sensors, proximal hyperspectral readings on the wet pasture before it's cut. We dry the pasture and do 400 hyperspectral tests on the dried pasture, and we have 400 soil samples. So we go 4 times a year. We have something 8,000 samples, so we have quite a lot of ground truth data, but we've gone back here and found areas outside the 400 to try and get some more validation on these NP-K maps. We have produced other maps, but the NP and K we've actually produced or have some more validation. That's an Emmy map. So this is looking at pasture quality. Pasture quality, high N and high K, seem to be very they have a high level of where you find one, you find the others, so but it's not the case the other way around. So we have not been able to get much soil information from our plant hyperspectral sensing. We know we have low soil fertility, we get low plant nutrient and low ME, but we cannot say that we don't have, it's not the other way around. So we have found areas where we have high soil nutrient and low plant nutrient. So we have been plotting our way through NDVI, NP, K, S, magnesium, and some measurements like dry matter, which we also validate through cuts, and we have cages on this farm. Now, we've been able to afford to do this because we have a private-public partnership. I think they're quite important. We have $10 million of US funding over 7 years to try and map nutrients. We are finding that we are able to map them in locations hundreds of kilometres apart. that the same prediction analysis lines apply on all properties. So we are not just mapping a nutrient on one farm, we're actually mapping these nutrients on several locations. I know it's not been fully validated, but we are getting around to validating it. We are having plenty of data collections. We will be continuing to do this over the next 2 years. We're off to the South Island next. We've done 4 North Island farms, and we're going to see if it applies in the South Island. All the wet chemistry prediction analysis results use partial least square regression to predict nutrients, and the dry samples, once we've got rid of the water, all have R-squareds greater than 0.9. So when we have 8,000 samples with an R-squared greater than 0.9, we're getting some quite good results. We have been extrapolating these wave bands with very high statistical significance over the whole farm, and we hope that this is a bit of a breakthrough, and that it should help with analysing crops in other countries, because if we can find the nutrient at many locations, it shouldn't matter whether that nutrient's in a multi-crop pasture, which we're doing, or a monoculture, such as a crop, for example, cassava. Thank you very much.